Greetings, this video is about the MiG-25. About the MiG-25 as it is. It is an aircraft created in the early 60s at the Mikoyan and Gurevich Experimental Design Bureau to perform, in various modifications, interception and reconnaissance and strike operations at high altitude. It was one of the great technical projects of the Soviet Union, an innovative aircraft in all aspects. It is the fastest air-breathing manned aircraft in the history of aviation. The great race for the highest airspeed has been waged by the world's leading powers since the dawn of the aviation era, and ended on March 6, 1964, when the MiG-25 took off from Ramenskoye airfield near Moscow for the first time. This video highlights in detail the supersonic characteristics of the MiG-25 and some of its world records. Some of the information contained here has never been published outside of Russia and never on the internet. You will learn a lot about this plane and maybe look at it with new eyes. This is an educational video that provides also the knowledge needed to properly understand these issues. This is important because the MiG-25 holds the record among aircraft for the number of myths and fakes written about it. It can be said that this is his 30th record, in addition to 29 world aviation records it set. So, let's get started. The speed of Mach 2.83, corresponding to 3000 km per hour and referred to in most publications as the maximum speed, is the maximum for operation in combat units. More specifically, it is an operational speed limitation at altitudes above 17 or 18, depending on the modification, kilometers, aimed at ensuring a certain resource of the airframe and tensions. In other words, it's not a thrust limit and not even the design limit. Now we will see what speed the MiG-25 can achieve at full afterburner thrust. This is the curve of the maximum energy altitude of the MiG-25 RBA. The right point corresponds to the speed and altitude of steady level flight at which the aircraft reaches a given energy altitude. All other points on this curve show the transformation of speed into height at which the energy altitude remains constant. Hence, at an altitude of just under 20 km, the speed of the MiG-25 RBA is Mach 3.5. That is 3720 km per hour in clean configuration, without weapons, pylons and external fuel tank. Now I will explain what energy altitude means. The total mechanical energy of an aircraft is equal to the sum of its kinetic and potential energies. However, it is impossible to get an idea of how fast and high an airplane is flying based on its energy, because weight is also an important component of energy. It is obvious that a heavy aircraft has a lot of energy even during takeoff, and that the energy of the aircraft in flight changes due to the decrease in fuel weight. Therefore, to determine the energy level gained by the aircraft only due to the changes in speed and altitude, the concept of energy altitude is used. This is the ratio of the total mechanical energy of the aircraft to its weight. So, energy altitude does not depend on weight. In American manuals, the energy altitude is often called specific energy. The energy altitude is the sum of the actual flight altitude and kinetic altitude. That is the height to which the aircraft will rise if at its current speed it heads up at a right angle, without taking into account the influence of thrust and drag. For each altitude and flight speed, the aircraft has its own energy altitude. For subsonic aircraft, which are relatively slow-moving, the actual flight altitude is a more significant component in the energy altitude. The faster the aircraft flies, the more the share of kinetic energy increases. For fighters flying at speed of more than Mach 2, the share of kinetic energy in the total energy is much greater than the share of potential energy. Therefore, they have the highest energy altitude not at the maximum altitude of steady level flight, that is not at the static ceiling, but at the area of maximum speeds, below the static ceiling. The energy altitude curve is the set of all points at which this altitude is constant, although its components at each point are different. In general, each such curve is bounded by a point of zero altitude and a point of zero speed, that is by boundaries at which one of the components is zero. On the curve of maximum energy altitude, there is a one point at which the aircraft flies with maximum energy in steady level flight. This and only this point is in contact with envelope, which is limited by thrust and not by other causes. Is the speed in point of maximum energy at the same time the maximum possible speed of horizontal flight? Approximately, we can say that yes. In fact, the aircraft can fly slightly faster, 142 km below the point of maximum energy. For example, envelope of the MiG-29. The point of top energy is Mach 2.3 at an altitude of 15.5 km, and the point of top speed at an altitude of 14 km. As you can see, from 12 to almost 16 km, the maximum speed is Mach 2.3, plus from 0 to 30 km per hour. This is negligible difference. An additional 30 km per hour to the maximum speed mattered for World War II aircraft, not for Mach 2.2 aircraft. Let's return to the MiG-25. The graphs in Soviet manuals also often show not the entire curve of the maximum energy altitude, but its upper part, which starts from the point of maximum energy of steady level flight, so that this point is immediately visible. It is this part of the curve that is shown on this graph. Another example of such a graph for the MiG-29. Its maximum energy altitude is 39,000 meters and corresponds, as mentioned above, to a speed of Mach 2.3 at an altitude of about 15.5 kilometers. This same altitude is shown on this graph. So, the maximum speed of the MiG-25 RB at an altitude of about 20 kilometers is Mach 3.5. The corresponding energy altitude is 74 kilometers. And this is for average long-term temperature over Moscow. I will explain the meaning of this clarification a little later. This is flight envelope of the MiG-25 RB, which is specified for all altitudes, only taking into account operational limitations. Now I will give an approximate view of the envelope corresponding to the maximum theoretical flight speed. We have two reliably known points. The point of maximum speed at an altitude of just below 20 km, Mach 3.5, and the maximum speed at sea level, about Mach 1.2. It is indicated on this graph and corresponds to the intersection point of the curves of required and available thrust. Required and available thrust is one of the main graphical methods for determining the maximum speed of an aircraft, along with a graph of maximum energy altitude and an envelope graph if envelope is limited and caused to zero excess thrust. For example, you have seen the envelope of the MiG-29 with a speed of around Mach 2.3 at an altitude of about 15 km, and the maximum energy altitude, which corresponds to same speed and altitude. In this graph, you see the same Mach 2.3 at 15 km as the intersection point of the required and available thrust curves. The faster it flies, the smaller the difference between the required and available thrust. That is, the curves converge, and at a speed of Mach 2.3 they intersect. The excess thrust becomes zero. This is its thrust speed limit, with two R-60 missiles and with a weight of 13 tons. So, here the speed of the MiG-25 at sea level is almost Mach 1.2, more precisely Mach 1.17, for a weight of 30 tons, that is with a fuel weight of 10 tons. With a lower fuel weight, the speed reaches Mach 1.2. Note that this point of the ceiling is not on the full envelope. Here, at an altitude of 23 km at a speed of Mach 2.6, the excess thrust, that is the difference between available and required thrust, is zero. But because this ceiling is achieved in accordance with the rules of training flights, in which the speed is limited to Mach 2.65. This should be explained. The maximum flight altitude of an airplane is related to its speed, because the lifting force depends on the speed. If you are performing a training flight on a supersonic aircraft, but have a mission to fly in this flight only at subsonic, then the static ceiling that you can reach even with full afterburner is this one, and here the excess thrust is zero, although the aircraft is capable of flying higher. In order to achieve the maximum possible static ceiling, the aircraft must fly at the speed at which they have the highest vertical speed. The vertical speed is equal to the flight speed multiplied by the excess thrust and divided by the weight of the aircraft. That is, at a given weight, for a higher vertical speed, the product of flight speed and excess thrust must be greater. Let's return to the MiG-25. According to the instructions, the pilot accelerates at an altitude of 20 km from Mach 2.35 to Mach 2.5-2.6 and reaches the ceiling at this speed, which is closer to the operational limitation for training flights. Here are the graphs of available thrust and required thrust for fully armed 30 tons interceptor, including at an altitude of 20 km, according to which we can find out the increase in excess thrust. It follows that as the MiG-25 accelerates towards its operational limit, its excess thrust continually increases. That is, the thrust increases faster than the drag. Indeed, from Mach 2.5 to Mach 2.83, the required thrust, which is equal to drag, increases by 1,100 kg force, and the available thrust increases by 1,600 kg force. Thus, at Mach 2.83, the vertical speed is 1.65 times more than at Mach 2.5. Therefore, when climbing beyond the limits, the ceiling will be higher and the entire ceiling area on the graph, depending on the flight speed, is located higher and to the right. As a guide for a more accurate designation of the envelope, we will take the following fact. The MiG-23 ML with two R-23 missiles accelerates to a speed of Mach 2.53, that is 2,700 km per hour at an altitude of 13-14 km. In clean configuration, the speed of the MiG-23 ML is at least 2,900, possibly up to 3,000 km per hour. That's how fast the MiG-23 was. The fastest single-engine serially produced airplane of all time. The MiG-25 at the same altitude will fly faster, once again based on thrust potential and not permissible air pressure. Here is the speed point of 2,900 km per hour at an altitude of 13 km, and the envelope of the MiG-25 is to the right of it. So, this is an approximate view of the MiG-25 Airbus speed limit in clean configuration, and that same curve of the maximum energy altitude. The upper, that is stratospheric part of this envelope, I repeat again, is given for average long-term temperatures over Moscow. Now we will talk in more detail about the excess thrust at a speed of 3,000 km per hour. The thrust required for steady level flight is equal to the drag of the aircraft, and it is also equal to the ratio of the aircraft's weight to its lift-drag ratio. The lift-drag ratio is one of the most important parameters of the aircraft. It is equal to the ratio of the aircraft's lift to its drag, and depends on the speed and altitude, and on everything that creates additional drag. Angles of attack and slip, the weapons, released landing gear, brake flaps, and so on. So, at a speed of 3,000 km per hour, at an altitude of 20 km, without weapons and pylons, the lift-drag ratio of the MiG-25 in level flight is 3.8. The thrust of one R-15B300 engine at the same speed and altitude is 5,800 kg force. This means that with a mass of 22 tons, the thrust of one engine is sufficient for flight at a speed of 3,000 km per hour at an altitude of 20 km. This does not mean that the MiG-25 can fly at this speed with one engine, because the asymmetry of thrust creates a moment relative to the center of gravity of the aircraft, to compensate for which the rudders are deflected, which increases the drag. But this means that with both engines running, the aircraft has an excess thrust equal to the full afterburner thrust of the second engine. That is 5,800 kg force, or almost 57 kilonewtons, which, with the given weight, at the moment of passing the speed of 3,000 km per hour, gives it an acceleration of 2.6 meters per second in 1 second. Just for example, this acceleration is much higher than the acceleration of the MiG-29 at a speed of 2,000 km per hour at an altitude of 11 km. The lift-drag ratio of the armored MiG-25 decreases, and accordingly the thrust required for steady flight increases. Nevertheless, being fully armored, the MiG-25 is capable of exceeding not only 3000 km per hour, but also Mach 3. In this graph, the upper envelope corresponds to the full afterburner of both engines for a fully armored interceptor. It is operationally limited to 3000 km per hour from an altitude of almost 21 to 17 km. That is, below 21 km, the thrust is sufficient for flight at a speed of over 3000 km per hour. It should be explained what full armament is. These are 4 Air-40 missiles, each weighing almost half a ton, about 6 meters long, with 2 pairs of wings with a span of 1.5 meters. Each Air-40 has its own pylon, which weighs about 200 kilograms and is more than 70 centimeters high. This graph shows the required and available thrust for the interceptor with 4 Air-40 missiles for an altitude of 18 kilometers. At this altitude, at a speed of 3000 km per hour, the available thrust is not equal to that required for level flight, but exceeded by 3700 kg force. Thus, at the moment of overcoming the 3000 km per hour at an altitude of 18 km, a fully armored MiG-25 has an excess thrust of 36 kN. It reaches its maximum speed at the intersection of these curves. On the graph, we don't even see a clear tendency for these curves to converge. The point of intersection is located to the right of the Mach 3. The MiG-25 airba with 4 FAB-500 bombs under the fuselage or under the wing is also capable of flying faster than 3000 km per hour. In general, supersonic weapons under the fuselage create much less drag than these same weapons under the wing. This is the case for all aircraft. The MiG-25 carries bombs on 2 holders, each with 2 bombs in tandem, which also reduces drag. As can be seen from the envelope, with a mass of 28 tons, such a flight, limited by Mach 2.83, is possible at altitudes from almost 22 to 18 km, where the indicated airspeed limitation comes into force. Actually, these are data from the MiG-25 airba test results with mock-ups of FAB-500 M62 bombs under the fuselage, identical in weight and dimensions. The speed with these real bombs is limited to a Mach 2.35 due to the heat resistance of the fuses. For higher speed flights, special FAB-500T heat-resistant bomb was created. And the holders of these bombs have also been modified, because the standard holders spontaneously dropped bombs during tests, when heated at high speed. With a small fuel reserve in clean configuration, the MiG-25 changes energy so intensively that it is impossible to guide it along a given trajectory, given that at high altitude aircraft control generally has a large inertia. The great test pilot Alexander Fedotov encountered this problem when he set an absolute altitude record in a zoom climb. I will talk about this in detail later. The viewers may think that the MiG-25 had amazing acceleration only at high supersonic speeds, around Mach 3. No, it had no equal in acceleration throughout its entire supersonic range. In the last part of this video, when I will compare in detail the time to climb records of the MiG-25 and F-15 Streak Eagle to an altitude of 30 km, you will see how much the MiG-25 surpasses the best 4th generation fighters in supersonic acceleration. As for the speed at minimum afterburner, for an interceptor with 4 missiles, it corresponds to Mach 2.55 at an altitude of 15.5 km and is limited by the indicated airspeed. For MiG-25 airba with 4 bombs, it is about Mach 2.7 at an altitude from 18 to 19 km. Cruising mode, that is the mode of the lowest kilometer fuel consumption, with a minimum afterburner corresponds to a speed of about Mach 2.35 at an altitude from 20 to 22 km. Now consider the effect of atmospheric temperature on flight speed. I have mentioned that this is flight envelope for long-term average temperatures over Moscow. This is the 56th parallel of north latitude. What's the point of this? Thrust and maximum speed at a given altitude are not constant values, but change with decreasing temperature and a corresponding increase in air density. In the first layer of the atmosphere, called the troposphere, the temperature decreases with increasing altitude. So the thicker the troposphere, the lower the temperature at its upper boundary. Above the troposphere, after a thin layer called the tropopause, the stratosphere begins, in the lower half of which the temperature varies little. Up to an altitude of 25 kilometers, it remains approximately the same as at the upper edge of the troposphere. The thickness of the troposphere and height of the lower boundary of the stratosphere is not the same for whole Earth. They increase from 8 kilometers at the pole to 17 at the equator. Therefore, the temperature of the stratosphere falls from the poles to the equator. It is minus 86 degrees Celsius at the equator and only minus 45 degrees at the poles. These are the average results of many years of measurements. The actual temperature and the position of the lower boundary fluctuate around these numbers within certain limits, depending on a number of factors. So, the closer to the equator, the colder the stratosphere, the denser the air and the greater the thrust of the engine. The same supersonic stratospheric aircraft in equatorial latitudes can fly many hundreds of kilometers per hour faster than in northern latitudes. This is the envelope of the F-15 showing the changes in speed, with a temperature deviation from a US standard day by 10 degrees Celsius in both directions. In the non-afterburning mode, the difference is minimal, but in the afterburning mode, a decrease of only 10 degrees leads to an increase in speed by 200 km per hour. The MiG-25 has an even greater increase in speed as the temperature drops than aircraft such as the F-15 or Su-27, precisely because of the peculiarity of its afterburner, which I will talk about a little later. With the ability to fly at a speed of over 3,700 km per hour at the 56th parallel, exceeding 4,000 km per hour, for example 20 degrees to the south, that is for example in Middle East or in California at Edwards Air Force Base, was no problem for the MiG-25 in terms of sufficient thrust. Now, using a specific example, we will see how a decrease in air temperature affected its speed. As you remember, the MiG-25 cruises with minimum fuel consumption per kilometer at minimum afterburner at altitudes from 20 to 22 kilometers at a speed of Mach 2.35. This is according to the Soviet manual. Having this altitude and speed, the MiG-25 RB perform a glazing flight at idle for a range of 250 km. The glazing range of an aircraft from point A to point B, with a gradual decrease in speed, is equal to the product of the loss of energy altitude and the lift-drag ratio. This is a maximum possible glazing range. This range should not be confused with the shorter glazing range at a constant speed, which is equal to the product of the lift-drag ratio and loss of altitude. The following slides contain the derivation of this formula, which can be skipped without prejudice to the assimilation of the main topic. But it is useful to study because it contains important concepts: energy rate of climb, longitudinal acceleration energy load, and shows their relationship. So, at a speed of Mach 2.35 at an altitude of 22 km, the initial energy altitude is 47,000 meters. The final, at the moment of landing, is 500 meters. Average lift-drag ratio of gliding flight is 5.37. The thrust at idle has no noticeable effect on the gliding range. It is extremely small, and in part of the trajectory it is even negative, due to the overexpansion of the gas behind the turbine. Now let's listen to what says about the gliding flight the Indian pilot and now retired Marshal Sumit Mukherjee, who was the commander of the 102nd Squadron.
At around 18 kilometers or so, we would come back from the max afterburner to min afterburner, minimum. You kept minimum afterburner for the rest of the mission.
Right, min burn.
Where the ambient temperature there is minus 85 to minus 90 degrees Celsius. Our skin temperatures, incidentally, at those speeds were plus 300 degrees Celsius. So at the end of a profile, typically, without touching anything, you would end up, because of the fuel having got consumed, end up at about 22 kilometers or 23 kilometers sometimes. So you came up at about 22 kilometers by the time you decide to get back. And now when you get back, you come back and you switch off the burners. And then you come to idle and you glide back home 350 kilometers of distance.
So, the Indian MiG-25 Arba, in accordance with the optimal long-range flight profile, after reaching cruising speed and altitude at full afterburner, switched to minimum afterburner, and was cruising with a gradual increase in altitude until the end of its mission. At the end of the cruising, when the altitude reached 22, sometimes 23 kilometers, it switched the engines to idle and glided to 350 kilometers. That is 100 kilometers more than the range of typical glazing of the MiG-25 according manual. During cruise, the aircraft heated up to 300 degrees Celsius, and the temperature outside was minus 85, minus 90 degrees Celsius. This heating temperature means that the speed was around Mach 3. At Mach 2.35, even for a long time, the temperature does not exceed 200 degrees. Let's determine the speed required for such a gliding flight. When gliding from an altitude of 22 km to a distance of 350 km, with a lift drag ratio of 5.37 and the final energy altitude of 500 meters, the initial energy altitude is 65,700 meters. That is, the kinetic altitude is 43,700 meters, which corresponds to a speed of 925 meters per second, or 3,330 kilometers per hour, at minimum afterburner. This is indeed about Mach 3, and 800 kilometers per hour exceeds the cruising speed of the MiG-25 Arba at the 56th parallel. The extremely low temperature outside in this flight, up to minus 90 degrees, explains why this was so. Before moving from the thrust achievable speed to the operational speed limits, I will mention the speed record on a 500 km closed road. On October 5, 1967, test pilot Mikhail Komarov set a record with a result of 2,981.5 km per hour. Since this is almost 3,000 km per hour and this is a record, most people understand this as evidence that this speed is maximum possible. In fact, the closed road consisted of straight sections and a U-turn. Before starting the road, the plane accelerated to a speed much higher than Mach 3, and then performed a U-turn at a speed that dropped to less than 3,000 km per hour. After exiting the turn, it flew in a straight line again, accelerating to a speed of more than Mach 3. According to Aviation Federation rules, a closed road is two or more points connected by straight lines. The aircraft must fly over all control points and return back. Above each point, it must fly no lower than above the first one. The length of a closed road is the distance connecting the control points over which the aircraft must fly. There can be 2 points, in this case the road length is twice the distance between them, or more, in this case a closed road is the perimeter of the polygon. The aircraft cannot turn with a zero radius, so the length of the trajectory is longer than the length of the closed road. According to the rules, the average speed on a closed road is the ratio of the length of the closed road to the flight time, and not the distance traveled to the flight time. Therefore, the actual flight speed is higher than the one that is counted as a result. Remember this, later we'll get back to the closed road. 10 years later, Svetlana Savitskaya on a training interceptor set a speed record on a closed 500 km road in the women's category. She was the only woman to fly a MiG-25 alone. The two-seat training MiG-25 PU has a modified nose section which creates about 10% more drag. It can also fly over Mach 3, and during the tests it flew with 4 missiles at a speed of Mach 2.75. Since training MiGs flew more often than combat ones, its speed was limited to Mach 2.65 to increase its resource. It was decided that Savitskaya could go beyond this limitation, but keep the limitation for combat aircraft. In this flight, the speeds were about 500 km per hour less than Komarov's speeds. The result counted as a record was 2466, and on straight sections the speed was about 3000 km per hour.
Светлана, расскажите, пожалуйста, о том, как проходил полет.
Полет выполнялся на самолете Е-133, серийном самолете, созданном ОКБ имени Артема Ивановича Микояна. Полет выполнялся на высотах около 20 километров. Выполнялся на скорости гораздо больше, чем две скорости звука. На отдельных участках скорость достигала около 3000 км в час.
As for the record on a straight road, according to rules, the aircraft must fly a straight section from 15 to 25 km long in two opposite directions, without deviating from declared altitude by more than 100 meters. Due to the fact that the trajectory of fast-flying supersonic aircraft is more or less subject to fluctuations in altitude, not all of them can fulfill this requirement. The MiG-25 belongs to such aircraft. Therefore, the MiG-25 did not attempt to set an absolute speed record in a straight line. However, Savitskaya set a speed record in the women's category. To achieve this, she had to fly at a speed around Mach 2.6, so that trajectory fluctuations were within 100 meters. Now consider the design limits. As you remember, I said at the very beginning of the video that the 3000 km per hour limit is used to ensure a given aircraft resource. So, what speed could the MiG-25 reach without the risk of damage? What do the flight results and testimonies of the aircraft's designers and test pilots say about this? As general designer Rostislav Belikov writes, exceeding Mach 3 reduced the service life, but did not lead to damage of the airframe or engine. Test pilot Boris Orlov writes the same. During testing, there were exits beyond Mach 3 without any consequences for the airplane. As shown above, the MiG-25 could not only exceed Mach 3, but in the best case bring it almost to 4 by thrust. It is clear that the faster any aircraft flew beyond operational limits, the more intensively its service life was exhausted. The highest known speed that the MiG-25 RB achieved was Mach 3.6. The reconnaissance flight of this Soviet MiG took place over Israel in cold stratosphere, and this speed was not the maximum in those conditions. In this flight, the Mach meter malfunctioned and the needle stood motionless at 2.8. Meanwhile, the plane was accelerating, and the heat reached such a magnitude that the sealant in the cabin began to smoke. Only then did the pilot reduce the speed. The MiG returned safely from the mission, but the melted sealant welded the canopy, which had to be opened outside with a crowbar. Based on the temperature to which the sealant was heated, the technical specialists determined the speed, Mach 3.6. The story of these reconnaissance flights, including the above-mentioned fact, was first published in 2002 in the Krasnaya Zvezda, the official newspaper of the Soviet and Russian Ministry of Defense. Many viewers are now surprised because the internet is filled with nonsense that the R-15 engines are so damaged at a speed of more than Mach 3 that they cannot be used in the future. Here is a typical example.
Every time a MiG-25 went Mach 3.2, its engines turned to junk and had to be scrapped.
This is said with such amazing confidence, as if this man personally sent engines for scrapping every time the MiG-25 went Mach 3.2. This nonsense was invented by a traitor who escaped to Japan on a MiG-25. No other source that cares about its reputation repeats this. For the sake of clarity, I asked the author of this channel what his source was, of course knowing the answer in advance. That's exactly the answer I got. The story that the Israeli radar operator allegedly told about the MiG flying at Mach 3.2 and that engines of this aircraft are out of order is a complete fiction. And it's not just about the myth of engines, but also about this very Mach 3.2. This is a crude fake. The operators of air defense systems do not measure speed of the target in Machs. It does not make sense to them. Mach numbers are important for pilots. Operators determine the speed in kilometers per hour, miles per hour, or meters per second. In the Russian open sources about these events, we can see that the Israeli radar operators mention speeds of 3,500 and 3,700 km per hour. The second speed corresponds to above-mentioned flight at Mach 3.6, taking into account that the radar determines the flight parameters of the high-speed aircraft with increased deviation. So, in reality, this problem does not exist. Not only the test pilots exceeded Mach 3. This happened systematically to the air defense pilots. The aircraft and engines have been checked and allowed to operate. Damage to the engines of the MiG-25 sometimes occurred, but it was not related to exceeding Mach 3 at high altitude. The reason for this was different, flying at high speed in dense layers of the atmosphere, when the engine is operating under enormous pressure, caused by ultra-high indicated airspeed, IAS. According to the instructions, the IAS limitation after equipping the aircraft with a differential stabilizer was reconnaissance bomber 1100 km per hour at an altitude of up to 18 km. Interceptor 1200 km per hour at an altitude of up to 17 km. For test flights of both modifications with a finally modified stabilizer, the limitation was 1300 km per hour, while there was still a large reserve of speed for safe flights. Here are some cases of an aircraft reaching an ultra-high IAS and overloading, after which the aircraft returned to the airfield. This is the objective control data of the flight recorders. In one of these cases, the interceptor reached an IAS of 1650 km per hour in the altitude range from 12 to 13 km. And the total time beyond the limit was 3 minutes and 10 seconds. This aircraft was approved for further operation after the replacement of engines. This is the example I mentioned above. At high altitudes, as you have already seen, this problem does not exist, because there are no indicated airspeed limits at high altitudes. The density and pressure of the air at an altitude of 12 km is 3.5 times greater than at an altitude of 20 km. At 20 km at a speed of Mach 3, the IAS is about only 1050 km per hour, and in order to reach 1650 km per hour, the aircraft needs to fly at hypersonic. In two other cases, the planes were written off. These cases were combined with a GLOT of 11 and 10, and the aircraft was damaged but not destroyed. I'll talk about overloads and maneuverability later. Now I am considering indicated airspeed. What was the IAS that destroyed the airframe? There was a crash of the reconnaissance modification due to the loss of consciousness by the pilot. The plane switched to descent and began to destruct upon reaching an IAS of 1760 km per hour at an altitude of 11 km. The high-speed pressure at that moment was 12,900 kg per square meter. Regarding the heat resistance of cockpit glazing, the MiG-25 was equipped with special heat-resistant glass, which was cooled from inside the cabin by streams of frosty air. The thickness of the front glass is 20 mm. If the plane does not exceed Mach 2.83, the front glass has a guaranteed service life of up to 10 years. If the plane flies faster, then the life of the glass decreases, but up to a certain limit the glass is still not damaged. This speed for long flights, depending on the typical air temperature in the Soviet Union, ranges from Mach 3.1 to 3.2. At an even higher speed, by a long time, so-called silver is formed on the surface of the glazing, a network of small cracks up to 0.5 mm deep. The glass does not break, but acquires an optical defect, and therefore such glass must be replaced. However, for a short time or for a long time in the cold air of more southern latitudes, the MiG-25 can exceed this speed without damaging the glass. Firstly, it is clear that the lower air temperature reduces the heating of the aircraft. But the main reason is different. The stagnation temperature in the boundary layer rises almost simultaneously with the increase in speed. This occurs because the kinetic energy of the oncoming air is converted mostly into thermal energy during stagnation. but the heating of the aircraft surface by heat transfer from the boundary layer occurs gradually. For example, the S-200 missile accelerates to a speed of Mach 6.5, and the stagnation temperature reaches 1500 degrees. But the missile itself manages to heat up to no more than 830 degrees Celsius. Because in order for the surface of an aircraft or missile to heat up to the stagnation temperature, it must fly for a long enough time. This time depends on the properties of the material and the shape of the aircraft surface, and, very importantly, on the air density, that is, on the flight altitude. With a decrease in air density, the viscosity coefficient increases, and as a result, the thickness of the boundary layer increases. Accordingly, the process of heat transfer to the aircraft occurs less intensively. For example, at a speed of Mach 3, an aluminum skin 2 mm thick will heat up to the stagnation temperature of 300 degrees Celsius in just 1 minute at an altitude of 15 km, but more than 8 minutes at an altitude of 30 km. This is why in colder air and at higher altitudes, exceeding Mach 3.2 even for a long time does not cause damage to the glazing of the MiG-25. In conclusion, I would like to note that for the MiG-25M, for which the operational speed limit was increased to more than Mach 3, it was planned to install the same glass. As for heating the fuel inside the tanks, I'll talk about it soon. And we will also return to the MiG-25M. Power unit, that is engines and air intakes, are most noticeable elements of the MiG-25. Visually, it consists of two huge pipes, and front part with a cabin and electronic equipment. At first glance, it is unclear where 15 tons of fuel are placed there, twice as much as on the heaviest American F-14 fighter. Now we will consider the principle of creating thrust by the R-15 engine. High-speed atmospheric flight implies high thrust. Meanwhile, the bench thrust of the R-15B300 is significantly less than that of the Al-31F, the engine of the Su-27, which is not capable of flying so fast. This means that the R-15 somehow generates very high thrust during flight. Usually those who talk about the MiG-25 try to explain it by saying that the MiG-25 had an adjustable air intake. Such intake in the entire speed range ensures equality of the amount of air passing through it and through the engine, and also equalizes the air pressure across entire cross-section before entering the compressor. This is true. MiG-25's air intakes are adjustable. However, adjustable air intakes are also installed on the Su-27 and on almost all supersonic aircraft exceeding Mach 2. The reason why the R-15 creates very high thrust is hidden in something else. Firstly, consider the change in pressure of gas passing through the typical jet engine of an aircraft flying at subsonic speed. Once in the air intake, the air experiences compression, which is small at subsonic and transonic speeds. Then the air enters a multi-stage compressor, where it is strongly compressed. Then the air enters the combustion chamber, where it mixes with fuel and burns under favorable conditions due to its high density, and thus the resulting gas acquires great potential energy. This gas then enters the turbine and expands and rotates the turbine, which rotates the compressor. Here most of potential energy of the gas is converted into kinetic energy of turbine rotation. As a result, the air pressure on the turbine drops sharply. Then the rarefied gas enters the afterburner chamber, where it mixes with fuel and burns again, since oxygen still remains in it. But this combustion, unlike combustion in the main chamber, occurs at a low gas density. Finally, the gas enters the nozzle from the afterburner. There, its potential energy is converted into kinetic energy of a gas jet, creating thrust. Thus, these engines are economical in non-afterburner mode and uneconomical in afterburner mode. But this is exactly what fighter jets need, which spends most of their flight time, including combat missions, in a speed range where the use of afterburners is very unadvantageous in terms of thrust relative to fuel consumption. Hence the designer's goal to provide the engines with as much non-afterburner thrust as possible, and ideally to provide non-afterburner supersonic flight. Now let's look at the R-15B300. This is an engine with a 5-stage compressor that provides compression of only 4.75 at bench, and a single-stage turbine, a lazy turbine according to the designers of this engine. Next you will see why this epithet is applied to the turbine. It is clear that at such compression this engine cannot be effective at subsonic. And due to the low air pressure at subsonic, a huge intake is required to supply this engine with air. That's why the area of the MiG-25 air intake is almost twice as large as that of the Su-27, although the L-31F has 10% more bench thrust than the R-15B300. But such slight air compression is the case only at zero or low speeds. As the speed increases, the air begins to compress more and more in the air intake. This is the formula for compressing the air in the air intake. K is the air adiabatic index, equal to 1.4. C0 is the air velocity at the entrance to the air intake, which is equal to the speed of the aircraft at zero wind. C1 is the air velocity at the compressor inlet. That has already become subsonic. T0 is the atmospheric temperature in Kelvin. So, at a speed of Mach 3, the air intake compresses the air 36 times. At a speed of Mach 3.5, 70 times. That is, air intake becomes a more efficient compression device than the most efficient compressor. At the same time, the compression ratio of the R-15 compressor decreases with increasing speed. At a speed of Mach 2.83, it is not 4.75, but only 2.4. At high speed, the following occurs in the R-15. The air is compressed mainly in the air intake, burns in the combustion chamber and enters the turbine, which is lazy. Typically, turbines are designed to rotate as fast as possible, and for this, they take from gas as much potential energy as possible. The R-15 turbine, so to speak, does not want to do its work. In fact, there is no point in this work, because there is no point in a compressor, because the air intake already does its work. This turbine takes only a small part of the gas energy, and the gas, retaining very high density, enters the afterburner chamber. There the gas burns for the second time and enters the nozzle, where it expands, creating a jet stream with unprecedented kinetic energy. To expand such a large amount of gas, a huge nozzle is needed, much larger than the nozzles of other jet engines. This is exactly what the nozzle of the R-15 is. It is so large that the two nozzles do not fit side by side, and the adjacent partitions are removed from them. Thus, the compressor is functionally reset to minimum, and the afterburner starts working as a ramjet engine. At a speed of more than Mach 2.5, the gas-air mixture entering the afterburner chamber of the R-15 from the turbine is in the same conditions as the air entering the combustion chamber of a ramjet engine from its intake. To illustrate how effectively the R-15 creates thrust at high speed, let's compare it with the R-35-300 engine of the MiG-23 ML. This is a very powerful engine with a bench thrust of 12,700 kg force. At a speed of Mach 2.2 at an altitude of 11 km, the thrust is slightly higher, by about 6%. Another example, the RD-33, engine of the MiG-29. At a speed of Mach 2.1 at an altitude of 11 km, its afterburner thrust is only slightly higher than on the bench. This is the afterburner thrust of the R-15B300. At Mach 2.2 at an altitude of 11 km, it is 17,000 kg force, which exceeds the bench thrust by 52%. And it exceeds the thrust of the R-35-300 at same speed and altitude by 3,500 kg force, having 1,500 kg force less bench thrust. At a speed of Mach 2.83 at an altitude of 20 km, non-afterburner thrust is only 600 kg force, and afterburner thrust is 5,800. The share of the afterburner in the total thrust is 90%. There is no other turbojet engine in history with an equal ratio. To better understand how perfect the R-15 was at high supersonic, we will compare it with the most powerful ramjet engine of all time. The RD-012U, the ramjet engine with a diameter of 1.7 meters for the LAT-350 strategic intercontinental cruise missile. This missile made of titanium and steel was the first technology in the world for very long duration flights at Mach 3 or more. It reached a speed of up to Mach 3.45 to Mach 3.5 and an altitude of more than 25 kilometers during tests. Its testing began in 1957. In March 1960, it covered 6,500 kilometers in 2 hours. It was an innovative and great project that was ahead of its time. It was cancelled in favor of intercontinental ballistic missiles. The LAT-350 was accelerated by 2 boosters to Mach 2.8 at an altitude of 18 km in standard conditions, and then the ramjet started working, after which the boosters separated. At this moment, at Mach 2.8 at 18 km, ramjet thrust was 7,750 kg force. The R-15 has almost the same thrust. It has a less afterburning thrust, which is natural. It has a slightly smaller diameter than the 012, both in the nozzle and in the afterburner chamber. And nevertheless, together with the thrust component created by the mechanical part and the main combustion chamber, the thrust was almost the same, 7,500 kg force at Mach 2.8 at 18 km. The fuel used by the R-15 was high-temperature T6 kerosene, created by improving the characteristics of T5, which was created for the LAT-350. Sometimes you can come across nonsense about this fuel. Supposedly it will boil and explode if the MiG-25 exceeds Mach 3. As I mentioned above, the LAT-350 flew for 2 hours at a speed of Mach 3 and reached Mach 3.5. The thin shell of this missile was the body of its tanks, as on the MiG-25, and the fuel did not boil, not explode. The T6 has another 10 degrees higher boiling point than the T5. How long can the R-15 run at high speed? In 1970, the test pilots of the Air Force were allowed to fly at a speed of Mach 2.83 for 8 minutes. The test pilots of the Design Bureau flew at this speed for up to 20 minutes, for example when setting a speed record on 1,000 km closed road in 1967. Now pay attention. The instructions for combat pilots limited flight time in the range from Mach 2.65 to Mach 2.83 only to 5 minutes, and only during real combat flights. In fact, as soon as the time came for real combat flights in 1971 to 1972, when Soviet MiGs made flights over Sinai and Israel, all restrictions were lifted altogether. Completing these missions required a full afterburner for 40 minutes. The chief designer of the engine, Fedor Shukhov, gave permission for the afterburner to work without any time restrictions. More than half an hour the flights lasted at speed of 3000 or more kilometers per hour. There were no incidents with engines. There are many things in this engine that are worth talking about in detail. For example, its unique digital control system or the legendary cooling system. But in this video, dedicated to the supersonic characteristics, I talked specifically about the thrust of the R-15. Now I will briefly talk about the design before talking in detail about supersonic maneuverability, altitude and rate of climb. You may have noticed that the MiG-25 looks unusual for a super-fast plane. One detail from its history. On the day of its first flight, a very large number of military and civilian personnel, everyone who had the right to be there, gathered on the airfield, attracted by the news of the extraordinarily fast plane. They expected to see an air-routine aircraft with highly swept wings pressed against the fuselage. One of the eyewitnesses recalled that it was strange and funny to see some kind of angular cart on large wheels, slowly rolling out of the hangar. The MiG-25 has a thin wing of moderate sweep, providing good performance at both subsonic and supersonic speeds. However, it should be noted that a wing with a large sweep is more advantageous in terms of achieving the highest possible speed, since such a wing has a larger effective chord and a smaller relative profile thickness, and therefore less pressure drag. For example, the MiG-23ML with a wing at a sweep angle of 74 degrees 40 minutes has a maximum speed by thrust of about 300 km per hour greater than with a sweep angle of 47 degrees 40 minutes. The creators of the MiG-25 did not worry about this. The available thrust provided the required speed and acceleration even with moderate sweep wing, which at the same time improved subsonic maneuverability and takeoff and landing characteristics. Thus, the MiG-25's design was by no means subordinated to achieving the highest possible speed. Subsonic performance was also matters. The wing is tilted down by 5 degrees to reduce redundant static lateral stability. When maneuvering, the wing bends upward under the influence of lift. Like this. At 5G, the wing rises by 70 cm and becomes flush with the air intake. The wide fuselage with two large air intakes created lift, which on takeoff was a quarter of the total lift, and increased with increasing speed. At 3000 km per hour, it was already half of the total, and with a further increase in speed, it exceeded half. Thus, the MiG-25, which at subsonic was a typical aircraft with turbojet engines and a lifting wing, transformed into lifting body with ramjet engines at a high supersonic. Two large vertical stabilizers provided it with sufficient longitudinal stability in entire range of speeds. They are spaced far apart to reduce mutual influence and tilted outward so as to form a right angle with the fuselage at the junction point. There are also fixed surfaces under the fuselage, which serve to increase stability at high speed and at angles of attack. Large wings and large span stabilizers, directed obliquely, not horizontally and vertically, caused the aircraft to be nicknamed Chertopoloch, that is, the Thistle. The airframe consists of 80% steel alloys. The unique feature of the MiG-25 is its lightweight. The alloys were so plastic that it was possible to create a thin and durable, but not brittle structure, weighing less than the typical mostly aluminum structure. The XB-70 bomber, like the MiG, was made of 80% steel, and it was very heavy compared to the B-52. with comparable dimensions takeoff weight and fuel weight, the airframe of the XB-70 weighed 58 tons, versus 37 tons for the B-52. In the West, there is a widespread myth that the steel MiG-25 is also very heavy. In reality, it had the lowest empty weight and the lightest airframe, of course in its weight class and not in the MiG-15 or the MiG-23 class. That is among supersonic aircraft with a takeoff weight about 40 tons. The empty weight of the MiG-25 is 20 tons. This table shows the empty weight and internal fuel weight of other aircraft of this weight class, F-111F, Tu-128 and TSR-2. The closest to it, the F-111F, weighed 1.5 tons more. The design with movable wing increased the weight of an empty aircraft by about 4%. That is, with a fixed wing, it would weigh about 800 kilograms less. This is still significantly more than the weight of an empty MiG-25. The weight of the airframe is equal to the weight of an empty aircraft minus the weight of all onboard systems, engines, avionics, power supply systems, hydraulics, and so on. Note that the weight of two R-15 engines exceeds the weight of two TF-30 engines of F-111 by 1,600 kilograms. That's how light the airframe of the MiG-25 was. At the same time, it was very robust. You have already seen a list of some similar incidents. I'll bring them back. All this data were recorded by the flight recorder and then studied by specialists from the Design Bureau's Aerodynamics department. Pay attention to this case. November 28, 1975. The pilot concentrating on chasing the target forgot about speed control. At an altitude of 13 km, the indicated airspeed reached 1,650 km per hour, which means a true speed of around 3,000 km per hour. Noticing the training situation, the pilot performed an 11G maneuver. After reducing indicated speed, he continued his mission and successfully completed it, locking the target by radar. After that, the plane safely returned to the airfield, although it was written off after that, due to the severe deformation of the wing skin. 11 Gs at 3,000 km per hour. It sounds like a maneuver of combat missile. It's very difficult to imagine that it was actually a manned plane that returned and landed safely. But it was exactly the plane, the only one in history that was capable of this. The MiG-25 could withstand any overload that its stabilizer could create. The destruction could occur only in two cases, either when reaching an extremely high indicated airspeed, as I mentioned above, or when several restrictions are simultaneously and significantly exceeded. For example, once the MiG-25 collapsed, having an indicated speed of 1,600 km per hour, 7G load, and roll rate of 240 to 280 degrees per second, at the maximum permissible roll rate of 90 degrees per second. Here is a recording of this disaster from the flight recorder. Taken individually, none of these violations could have caused the plane to crash. The pilot ejected, but died. Even today, no ejection seat can ensure the pilot's survival at such an indicated speed. Even K-36DM has an IAS limitation for safe ejection of up to 1,400 km per hour. The G limit for the reconnaissance modification introduced to ensure a certain airframe resource was 3.8. The limit for the interceptor, introduced for the same reason, was 4.5, with 4 missiles with a fuel reserve of 5.5 tons or less. With a weight of 40 tons and a full fuel weight of 20 tons, together with a huge external tank weighing almost 5 tons, for the reconnaissance modification the operational overload was 2.7 G. For an interceptor with an almost full fuel reserve of 14 tons and with 4 R-40 missiles, the operational limit for combat flight was 3.4 G. You may have seen information that with a full fuel tanks, the interceptor's load is limited to 2.2 G. This is another fake about the MiG-25. With a weight of 30 tons with 4 missiles, the operational limit was 4.2 G, and this overload is available at sea level and at an altitude of 20 kilometers. However, the 4.5 G limit could be exceeded at least 1.5 times, that is up to 7, without damage to the airframe. For comparison, the Mirage 3C light fighter was irreversibly deformed by 8 G. That is, the difference in this case was not very large. Another example of nonsense published not long ago in a popular newspaper. Allegedly, with large overload, the missiles fall off the pylons. In reality, overload restrictions have nothing to do with this. The MiG-25 repeatedly went with missiles to large G-load, far exceeding the limits. Once there was a case when the missile engine started under the wing and worked until the fuel was completely consumed. The missile remained in its place, despite the fact that it was subjected to a thrust force of almost 50 kilonewtons for more than 6 seconds. The pilot showed great restraint. He did not eject, but calmly compensated for the thrust asymmetry by deflecting the radars, not knowing whether the warhead would detonate or not. He just hoped for the best and wanted to save the plane. And as it usually happens, there was a happy end, because the MiG-25 was a very reliable aircraft, and the same applies to its armament. Let's return to high-speed maneuverability, in which the MiG-25 was second to none. On April 8, 1973, Alexander Fedotov set a speed record for a 100 km closed route. This record, being little known to a wide audience, is one of the most difficult and outstanding records of the MiG-25.
Шеф-пилотом ОКБ, героем Советского Союза Александром Федотовым, было установлено 16 мировых рекордов. В их числе феноменальный рекорд скорости на замкнутом 100-километровом маршруте 2605 км в час и абсолютный рекорд высоты 37 650 метров.
Now I'll tell about it in detail. These are the parameters of this flight. The deflection angles of the ailerons and stabilizer, the weight, longitudinal and normal G-load, Mach numbers, indicated airspeed and altitude. By the way, this has never been published outside of Russia and never on internet. Now you are seeing this for the first time. So, the flight lasted 138 seconds. Most of the route, 2 minutes long, was a so-called loop, that is turn, with an average G-load of 4. The average speed during the entire flight was 2,730 km per hour. The flight took place in a Russisch called Pelena. This can be translated closely in meaning as haze. It is an unsteady flow around the air intakes that occurs when the MiG-25 is maneuvering at high altitudes. And the more intense the maneuver, the more intense the haze. It can also occur in straight-line flight at maximum speed in the altitude range from 14 to 18 km. The haze creates constant shocking of the plane, which significantly reduces speed. It also tires the pilot. Nevertheless, from start to finish, the aircraft, often referred to as a flying brick, managed to increase altitude by almost 2.5 km and speed by more than 300 km per hour, from Mach 2.6 to Mach 2.9. Once again, with a 4G turn, with an average bank angle of 75 degrees, in a non-stationary airflow. The maximum G-load on the road reached 4.7, and the minimum speed did not fall below Mach 2.4. The distance traveled was 104.7 km. The result counted as a record registered for 100 km road was 2,605.1 km per hour. This flight was the greatest demonstration of maneuverability at high speed in the history of aviation. This is a report by Fedotov himself about this flight. You can pause the video and read. You probably have questions. How was the aircraft modified to set records? Was any serially produced plane capable of making such flights? In the West, 99 out of 100 people who tell you about the MiG-25 will confidently say that it was heavily modified, without actually having any knowledge about this. The reality was this. 6 MiG-25s were used to set the records. 3 of them were the first prototypes, which were designated Ye-155 in the design bureau, and had the public designation Ye-266. They set records from 1965 to 1973. 2 MiG-25 Serba with more powerful engines set time to altitude and altitude records in 1975 and 1977. They had bureau designation Ye-155M and received public designation Ye-266M. And another aircraft, the training interceptor MiG-25 PU, with the designation Ye-133, on which records were set in the category for women. The largest number of records, 13, was set by the reconnaissance prototype Ye-155R3, built in 1966. It was this aircraft that set a record on a 100 km closed road, as well as records on closed roads in October 1967, and records for altitude and time to altitude in the summer of 1973. Here is the work that was done with this very aircraft, before the records. The only design change. Before the flight on a 100 km closed road, 2 anti-flutter rods were installed on the wings. This makes it possible to increase the indicated airspeed limit. You will say that any combat MiG-25 had these rods. That's right, it's just that this prototype did not have them initially. Thus, this change did not increase the difference between the record-breaking aircraft and the combat one, but on the contrary, eliminated it. Besides it, the following was done. The pilot's survival kit bag was removed from the cabin. Instead, a parachute device with an oxygen cylinder was installed to maintain pressure in the cabin at a very high altitude, when the cabin pressurization stopped. And finally, an oscilloscope was installed on the plane to record the flight altitude. This was simply an additional measure. Because according to Aviation Federation rules, only the results of the synod-analyzed survey are used to determine the altitude. If in one fine day you visit the Central Air Force Museum in Monino, near Moscow, you will see Ye-155R3. It has been an exhibit at the museum since 1979. Although the information plate says that it is just a MiG-25 Arba, without specifying its real history. Its tail number is 25. Do not confuse it with another MiG-25 there, an interceptor with tail number 04. This graph shows a typical dependence of steady flight speed of a supersonic aircraft on altitude. The section up to the first Mach is the minimum speed limited by the angle of attack. Below this speed, due to the violation of the normal flow of the aircraft, stable flight is impossible, even at the maximum angle of attack, and the aircraft stalls. In other words, this is the minimum permissible flight speed. The section from 1 to 2 is the minimum speed at high altitude limited by thrust. That is, this is not the minimum permissible, but the minimum possible speed of steady flight. The section from 2 to 3 corresponds to a decrease in altitude in the transonic range. This decrease is typical for supersonic aircraft. The reason for this is that at point 2 the drag becomes higher than the thrust. Mark 2 is called the transonic or subsonic ceiling. Some aircraft, such as the MiG-25 or MiG-23 at the maximum wing sweep angle, at high altitude have a thrust that exceeds the drag in the entire transonic range. They do not have a transonic ceiling. The section from 3 to 4 is also a section of the minimum possible speed limited by thrust. At the same time, there is a minimum speed limited by the angle of attack, which is less than the minimum speed by thrust. Let's remember this. The entire section after point 4 is the maximum speed limited by thrust. Here the thrust is equal to the drag. At each point the aircraft can neither accelerate nor make a steady climb. Point 5 is the point of maximum energy. Point 4, at which the minimum and maximum speeds coincide, is called the static ceiling. The static ceiling is the maximum possible altitude for steady horizontal flight. That is flight with a constant speed. Below this point, at all altitudes, there is a range of flight speeds. At the static ceiling, it is 0. There is no excess thrust, so the rate of climb is also 0. Flight at the static ceiling is practically impossible, because with zero excess thrust, the aircraft cannot compensate for any accidental decrease in speed. Therefore, the practical ceiling is matters. The altitude at which the aircraft has a minimum excess thrust sufficient to perform a reliable horizontal flight. It is accepted that at the practical ceiling, excess thrust should be enough for a vertical rate of climb at a speed of half a meter per second. I'll remind what I talked about in the first part of this video. Airplanes reach a static ceiling at a flight speed at which they have the highest vertical speed. For supersonic fighters such as the MiG-21, MiG-29, Su-27, F-15 and so on, this speed is approximately Mach 1.7, Mach 1.8. This speed is within their operational limits, so they reach their static ceiling without any problems. But the MiG-25 reaches its maximum static ceiling beyond operational limits, since with increasing speed, its excess thrust at an altitude of 20 km increases up to the operational limit of Mach 2.83. Within the operational limited speed for training flights, the practical ceiling of the MiG-25 RBA is 23 km, with a fuel weight of 3,400 kg. Another reason for increased thrust is cold air, which also affects flight altitude. A 10 degrees Celsius decrease in temperature leads to an increase in the ceiling by 600 to 700 meters. You saw from the story of the Indian pilot how the Indian MiG-25 cruised in very cold air with minimum afterburner at an altitude of up to 23 kilometers. So, the static ceiling is the maximum altitude for steady horizontal flight. However, above the static ceiling, the aircraft is also capable of flying horizontally, but with deceleration and only for a certain time. In our example, the maximum energy is at Mach 2.3 at an altitude of 15.5 km. The corresponding maximum energy altitude is 39 km. Let's plot the curve of this energy altitude. Let's plot the curve of the minimum permissible speed, which is limited by the angle of attack. It is specified in the flight manual for each aircraft, and usually is in the IAS range from 200 to 400 km per hour. The point at which both curves intersect is called the dynamic ceiling. In our example, it is 24 km. If the aircraft, having gained speed, makes a climb and rises above the static ceiling, it will be in the area of dynamic altitudes, and will be able to fly horizontally with deceleration for some time. For example, at an altitude of 20 km, the initial speed will be equal to the speed corresponding to the energy altitude of 39 km. And the final speed will correspond to the intersection of this horizontal with the curve of minimum speed by the angle of attack. At this altitude, the aircraft can fly horizontally until its speed decreases from Mach 2.1 to 1.3. The higher the horizontal flight with deceleration, the shorter its distance, and at the dynamic ceiling it turns into zero. The duration of the flight depends on the thrust and the aerodynamics. Any maneuvering increases the drag and reduces the flight duration in the dynamic altitude area. Most supersonic aircraft can rise from 2 to 3 km above the static ceiling and fly there horizontally for 3 to 4 minutes before descending. So, the dynamic ceiling depends mainly on the energy altitude that the aircraft has. Here is shown the dynamic altitude area of the MiG-25 RBA, taking into account the operational limited speed, which this energy altitude corresponds to. The dynamic ceiling here is approximately 28 km. At maximum speed limited by thrust, it is about 30 km. Above the dynamic ceiling, only flight with no horizontal section is possible. The maximum altitude depends on the speed and altitude reached before zoom climb, as well as the intensity of the maneuver, controllability and stability of the aircraft during the climb, and a specific airflow around an aircraft that may occur during maneuvering. In July 1973, the MiG-25 set an absolute record in this type of climb. At that time, the record was 34,714 meters, and belonged to the MiG-21, which was equipped with an additional rocket engine. To set an absolute record, it was necessary to exceed this record by 3%. That is to reach 35,755 meters. According to the calculations, which was based on the standard operational speed limit, the plane should have accelerated to Mach 2.83 at an altitude of 17 km and make an ascent with a load of 2.5. At the top point, it had a speed of Mach 1.15. As you already know, the MiG-25 can reach its maximum energy at an altitude of about 20 km. Theoretically, this allows to make the best zoom climb. In reality, the acceleration level is much lower than 20 km. The reason is that such a fast and high-flying aircraft cannot start climbing abruptly, unlike subsonic aircraft. On the contrary, it rises along a circle with a larger radius, gradually increasing the angle of ascent. If the aircraft begins zoom climb at an altitude of 20 km, it will soon be in an area of such thin air where the stabilizer's effectiveness will no longer be sufficient to increase the angle of ascent. As a result, this angle and consequently the vertical component of the speed will be small, despite the high total speed. When starting from a lower altitude, the aircraft will stay longer in denser air and will have time to gain the required angle of ascent. Let's go back to the record-breaking flights. The problem was that it was almost impossible to fulfill the theoretical conditions. The aircraft with a minimum fuel reserve had such excessive thrust that simultaneously with acceleration it sharply gained altitude. That is, even before the start of the zoom climb, its trajectory was directed upward. It could not just accelerate in level flight to the desired speed and then make a zoom climb. Moreover, acceleration and zoom climb took place in conditions of unsteady flow, which I have already described. It was impossible to calculate the actual speed loss. All this was further complicated by the fact that the aircraft has more inertial control at high altitude. By the way, the same problem was on the 100 km closed road. You have already seen the real parameters of this flight, and these are the speed and G loss that were calculated on the computer. You can see how much they differ from the real ones, and this is despite the fact that it was piloted by test pilot with excellent reflexes. So, 3 flights were performed, and each one was significantly different from the calculated one. On the first flight, the zoom climb began at an altitude of 15,500 meters at a speed of Mach 2.78 at an indicated speed of almost 1,300 km per hour. The result was 35,718 meters, slightly less than necessary. In the second flight, the aircraft reached Mach 3 according to this diagram, or 3.1 according to Fedotov's report, that you are about to see, at an altitude of 18 kilometers, and lifted with a G-load of 2.9. In this flight, the intensity of the haze was particularly strong, the loss of speed was greatest, and the aircraft reached an altitude of 35,500 meters, less than on the first flight, despite the better initial conditions. In the third flight, at Mach 2.6 at 14 kilometers, it performed climb with a G-load of 3.8. In less than a minute and a half, it reached an altitude of 36,240 meters. The speed there was Mach 1, and the indicated airspeed was 75 km per hour. An absolute record has been set. This is Fedotov's report on these flights. Pause the video and read if you are interested. Four years later, on August 31, 1977, the MiG-25M set a new record, 37,650 meters. It was a modification of the MiG-25 RB with more powerful engines, R-15 by F-2-300, with bench thrust of 13,500 kg force. It is worth noting that on July 22, 1977, two altitude records were set, 37,080 meters with a payload of 1 and 2 tons. This means that the MiG landed with a fuel reserve of more than 2 tons. Every 100 kilograms of fuel reduces the altitude by 40 to 50 meters. That is, without this load, the aircraft would have risen to an altitude of about 38 kilometers. The lift trajectory and flight parameters in this flight were more advantageous than in flight without a payload. The absolute altitude record is the most famous of the records of the MiG-25. In fact, any MiG-25 could set it. This record was set not due to more powerful engines, but due to pilots' experience gained in flights in 1973. It's just that the MiG-25M was at the flight base at that time, and therefore it was decided to use it for new altitude records. Its more powerful engines were really needed to set other records, new absolute time to climb records that at that time belonged to the F-15. I will now tell about this. Time to climb records are set to demonstrate the specific excess thrust of an aircraft. Specific excess thrust is directly related to the ability to accelerate. Besides, an optimally matched ratio of specific excess thrust and speed allows the aircraft to achieve maximum speed of steady climb. In short, this means the rate at which the aircraft can increase its energy, which is one of the key parameters of fighters and interceptors. In order to set a time to climb record, an aircraft must be able to acquire a certain amount of energy faster than anyone else in the world. The higher the altitude to be reached, the more energy is required. At an altitude of up to 15 kilometers, the aircraft rises in steady climb, at almost constant high subsonic speed. For records at altitudes of 20 kilometers and above, the aircraft must first accelerate to supersonic, and then make zoom climb, exchanging speed for altitude. A special position have the record of the time to altitude of 30 kilometers. To set it, the aircraft must make a world's best acceleration throughout a very large range of speeds, from 0 to more than Mach 2. In June 4, 1973, the Ye-155R3 set records for 20, 25 and 30 kilometers, beating the previous records of F-4H1. In the winter of 1975, one of the prototypes of the fourth generation F-15 fighter, called Streak Eagle, broke these records. We live in the era of artificial intelligence. Let's hear what it has to say about it.
They would climb higher, faster, and harder than any Soviet aircraft ever had. No missiles, no guns, just raw American engineering against Soviet propaganda. The world was about to witness whether the F-15 could truly soar past the myth of the Foxbat. And when the Streak Eagle's engines ignited and the earth trembled beneath it, America was ready to reclaim the sky.
Let's take a closer look at their records at an altitude of 30 kilometers. The MiG-25's plan was to reach high subsonic speed at low altitude, then climb steeply to an altitude of 4 kilometers, then reach supersonic speed in a gentle ascent at an indicated speed of 1,200 kilometers per hour, and then gain altitude trying to maintain this IAS before the start of the zoom climb. These are the parameters of the MiG-25's record flight. In the West, only a few people have seen this so far. Several Frenchmen from the International Aviation Federation and several specialists from the McDonnell Douglas. And maybe, I am not sure, pilot of Streak Eagle. Pay attention to the supersonic acceleration and ascent. From Mach 1.1 to Mach 2.2, it accelerated in 86 seconds, gaining 8.7 km altitude at the same time. For comparison, the F-15 accelerated in the same range from Mach 1.1 to 2.2 for 95 seconds, gaining 1.5 km at the same time. After another 25 seconds, the MiG reached a speed of Mach 2.5, and was at an altitude of 16 kilometers. From here it made a zoom climb with an load of up to 5.2. At an altitude of 25 kilometers, when the indicated speed was 400 kilometers per hour, the pilot began to reduce the slope of the trajectory. It reached a maximum height of 31,500 meters. 30,000 meters were reached in 244 seconds. This is a report by test pilot Pyotr Ostapenko about this flight. Note the non-optimality of the trajectory. During acceleration, it gained much more energy than required to reach an altitude of 30 kilometers. Firstly, it could have started the zoom climb half a minute earlier, with a lower speed and height, and this would eventually have given a time gain of about 20 seconds. Secondly, the pilot brought the plane out of the zoom climb already at an altitude of 25 kilometers. This was also a waste of time. Why was all this done? In fact, the pilot was not worried about time, because the previous record set by the Phantom was 6 minutes 11 seconds. The MiG-25, even with such time losses, exceeded it by more than 2 minutes. This was a standard trajectory for climbing to an altitude of 30 kilometers, and the pilot, having a high speed, carried out a smooth climb and a smooth descent. The McDonnell Douglas specialists who were preparing the F-15 for records certainly understood that the MiG-25 could reach this altitude much faster than it did, and it is not enough for the F-15 to simply beat this record by the minimum required 3%. The MiG-25 would return and set a new record. Therefore, the F-15 trajectory was optimized as much as possible. I will comment on it briefly. The most advantageous acceleration of the F-15 at supersonic occurs at an altitude from 10 to 11 kilometers. Therefore, the task was to reach this height combined with Mach number of about 1 as quickly as possible, while the task of the MiG-25 was to reach supersonic speed as quickly as possible. The F-15, like all fourth-generation fighters, could not compete with the MiG-25 in supersonic acceleration. You have already seen this. It was also inferior in the zoom climb, firstly because it had to turn into an ascent from horizontal flight, and the MiG-25 already had a certain trajectory angle before the start of the zoom. Secondly, the MiG-25's engines have much more thrust at supersonic and work longer at higher altitudes. That is, they transmit a greater force impulse. The bet was on gaining a key advantage at the subsonic stage of flight, where no aircraft could compare with the F-15 in the first half of the 70s. Before the start, the F-15 is held in place by a cable. Thus, it has the opportunity to turn on the afterburner and wait for the afterburner to reach maximum thrust, which takes a few seconds, and only then it starts moving along the runway. A standard takeoff is not only not profitable, but also impossible, because the landing gear brakes cannot hold it in place. For the F-15, the optimal trajectory was a climb with 3 horizontal acceleration sections. Immediately after takeoff, it made a short acceleration and climbed to an altitude of almost 9,800 meters by Mach 1.1, performing the Immelmann and turning the aircraft over. During the transition of the aircraft from vertical to horizontal flight with no turning, a long-time negative G-load would occur, which would lead to the cessation of fuel supply to the engines. For this reason, the aircraft can be in negative overload for only a few seconds. For example, for Su-27, this time according its manual is 3 seconds. Turning the aircraft over made it possible to avoid this problem and fly with a positive normal overload. Then the F-15 accelerated horizontally at this altitude. Then, when it passed the transonic range, the excess thrust increased, and it used this to gain another 1.5 kilometers to an altitude of 11,200 meters, where it is more advantageous to accelerate to a speed of Mach 2.2. After that, F-15 made a zoom climb to an altitude of 31,400 meters. It was the same altitude as the MiG-25, but because the F-15 was climbing while it was possible, and the MiG-25, as you remember, began to reduce the angle of inclination at an altitude of 25 kilometers. The F-15 reached an altitude of 30 kilometers in 3 minutes 27.8 seconds. This was a great result, 36 seconds better than the MiG-25 time, and the F-15 team was now confident that no one would surpass it in the foreseeable future. But since they did not know the MiG-25 well, they were mistaken. 3.5 months later, on May 17th, this record was broken. This time the trajectory of the MiG-25M was optimized. The acceleration with the climb lasted as long as necessary and was faster since the thrust was greater. The climb trajectory was steeper, which optimized the transition to zoom climb. The zoom climb was performed as steeply as the stabilizer efficiency allowed. In 1973, the MiG-25 was held on afterburnerless mode by the wheel brakes and started moving simultaneously with the start of the afterburner. As I said before, it wasn't optimal, especially for the R-15 engine, which was low responsive. The MiG-25M was fixed motionlessly with the help of massive wooden wheel chocks, which were fixed between the concrete slabs of the runway. Its engines reached full thrust, and then the plane began to move. As a result of all these measures, the time to reach an altitude of 30 kilometers decreased by 55 seconds compared to the result of 1973. 3 minutes and 9.85 seconds. It was 18 seconds better than the time of the F-15. On the same day, new climb time records of 25 and 35 kilometers were set. Note two circumstances. First, the R-15 by F-2300 was not an engine that had its thrust increased at the expense of its service life to set a record. It was a new modification, more powerful and more economical, which was to be produced in large series if the MiG-25M had been accepted into service. Simply put, it was not improvisation, but another achievement of the Soviet engine industry. Second, despite the fact that the MiG-25M was an improved version, it was nevertheless a third-generation fighter, and it broke the records of the newest fourth-generation fighter. This in itself is an outstanding event. Sometimes it happens that a new aircraft is inferior to its predecessor in same characteristics, but usually this means that these characteristics are not the main ones for the new aircraft. For example, the B-52 has a longer range than the B-1, but the B-1 is a bomber of different concept of combat using, originally designed to perform a mission with several air refuelings, designed with a more stronger airframe, with a significantly larger overall volume of weapons base, and so on. If the Rockwell engineer's goal had been to outperform the B-52 in range, it probably would have been done. But in the case of rate of climb records, we are talking about the most important characteristic for a fourth-generation fighter, the aircraft's specific excess power. Western sources will not tell you all this. Most of them won't say at all that the MiG-25 returned and broke the F-15 records in the same year. Those who mention this will say that this MiG was an experimental aircraft specifically for setting records and of course for propaganda purposes. In the worst case, they hint that the Russians used the rocket engine for assistance. This is a page from the official website of the American Department of Defense. I could comment on the form and content of this and generally talk at length about propaganda in the United States and the Soviet Union and their differences. But I won't do that now. Let's get back to the MiG-25. You probably have a question. Why didn't the R-15 by F-2300 enter mass production? The reason was this. At that time, the Perm Engine Building Design Bureau was developing a new engine, a turbofan with afterburner bench thrust of more than 150 kilonewtons, high pressure with a bench compression ratio of 22, with extremely high temperature in front of the turbine, multi-mode, capable of providing a long flight at a speed of 2,500 to 3,000 km per hour, and at the same time economical at subsonic. Such engines have never been created anywhere. It contained huge technical risks. The Central Institute of Aviation Engine Engineering gave a negative conclusion of the possibility of implementing this project. The new modification of the R-15 was created as a backup option if the PERM engine failed. However, the PERM Design Bureau solved all the problems, and in 1975, the new engine, the 30F6, was ready. Two MiG-25 Sarba were converted for flight tests of this engine. And then, on September 16, 1975, the next generation interceptor and next level weapon system, for which the PERM engine was intended, made its first flight. Finally, we will talk about the time to climb record for an altitude of 20 kilometers, which for some reason was considered the most prestigious by Soviet pilots. The current record was set in 1975 by the F-15.
By the way, this is the only record the airplane still holds. The Russians have broken all the others in subsequent years, but the F-15 still holds the 20,000 time to climb record. And I have no idea why they didn't break this one.
The first Soviet attempt to set this record was made in 1967, to mark the 50th anniversary of the October Revolution. The record was to be set by pilot Igor Lesnikov, an experienced test pilot of Air Force. He piloted one of the MiG-25s during their first public demonstration in Moscow in July of this year. He completed two preliminary flights surpassing the record of F-4H-1. But during the flight, in order to set an official record on October 30th, he exceeded the 1000 km per hour indicated airspeed limit. This limit was set for the prototypes that were not yet equipped with a differential stabilizer. This led to an aileron reversal, a strong roll, and a sharp turn toward the ground. The pilot tried to save the plane and ejected too late. This was the first crash of the MiG-25 and the first death of pilot on this plane. This is a timekeeping of this flight, which Fedotov made in his diary. After this disaster, the setting of records in MiG Bureau was postponed for ethical reasons. Then there were other accidents, and their investigation delayed the resumption of record flights. It's been 6 years. On June 4, 1973, test pilot Boris Orlov set a new record, 169.90 seconds. The beginning was the same as at altitudes of 30 and 25 kilometers. The zoom climb should have been performed earlier and with an overload of only 1.5 G. You can see the real flight parameters here. On January 19, 1975, the F-15 broke this record with an outstanding result, 122.94 seconds. The goal was to achieve a time of 126 seconds. Actually, it took 3 seconds less. In May 1975, the MiG-25M aimed to break this record too. As you understand, it was much more difficult than breaking records at altitudes of 30 and 25 kilometers. Because the speed to which the aircraft should accelerate is lower, that is, the greater the share of subsonic acceleration, in which the F-15 was better. The theoretical climbing time for MiG calculated by the computer was 122.8 seconds. It was slightly better than the F-15's time, but not enough to officially break its record. But the main problem was that this was a theoretical result, and the real time would have been a few seconds greater. And this is exactly what happened during 2 flights performed by Orlov. The experts of the aerodynamic department of the design bureau were skeptical about the possibility of setting a new record. And Fedotov too. But test pilot Valery Minitsky, who later became a chief pilot, really wanted to at least slightly surpass this record, and he believed that it was possible. He made some changes to the trajectory, by changing the conditions that the computer adhered to. In addition, the flaps were removed from the wing. This reduced the takeoff time on the runway by half a second to less than 6 seconds, and the landing gear cleaning speed was doubled. The goal has been changed, not to break the record officially, but only to surpass it. Several flights were made, and the best time was only 0.2 seconds longer than the time of the F-15. That is, from the moment the plane took off from the runway, it made climb faster. But, as you remember, the movement of the runway is also taken into account. The F-15 took 4 seconds to run, and the MiG took about 6. And thus the F-15 record was not exceeded, let alone officially beaten. Nevertheless, the MiG-25M showed a remarkable result. It is clear that with a lag of 0.2 seconds from the modified F-15, it was ahead of any other Western fighter of the 4th generation. In passing, in one of the last flights to an altitude of 20 kilometers, the MiG, continuing the climb, reached an altitude of 25 kilometers 7 seconds faster than on May 17th, when the official record was set. But the result of this training flight has not been officially registered. The time to climb records at lower altitudes were broken by these yellow-green aircraft in the 80s. But that's a completely different story. Here is what I wanted to tell you about the supersonic characteristics of the MiG-25. I hope that some of the difficulties in understanding my speech have been offset by the value of the information, and that this video has brought you closer to a correct understanding of one of the greatest aircraft in the history of aviation. Thanks for watching. All the best.